In this video, we're going to look at a basic introduction to trig equations. I'm going to choose one particular approach to solving these equations. If you've got a different way, you're more than welcome to use this. I'm going to stick with my particular method as it will solve all of the trig equations that we come across. The way I'm going to start this video is by looking at three different graphs. We've got the graph of y is equal to sine x, y is equal to cos x, and y is equal to tan x. Let's just look at some key features now of y is equal to the sine of x. This cycles every 360 degrees or 2 pi radians. We need to be comfortable with using both degrees and radians when we're solving these equations. So it does one complete cycle. It will continue infinitely in each direction. This point here is going to be 0 degrees or 0 radians. This is going to be 90 degrees, or we can write that this is pi by 2 radians. This point just here is 180 degrees, or pi radians. This point right here is going to be 270 degrees, or 3 pi by 2 radians. This is going to be the 360 degrees, and we would write that that is 2 pi. We could go backwards, we could have negative 90 and negative pi by 2. We could have now negative 180 and negative pi. This point is going to be negative 270 or negative 3 pi by 2 and negative 360. Okay, let's say we were asked to solve an equation. The equation I'm going to just try and solve is that sine x, let's write this here, sine x is going to be equal to now 1/2. This is going to give us a nice solution. Now I would want to first, I might be given an interval, I might be given the interval that I need to solve this between 0 and 360 degrees. If I get now a line and draw across, that is now where sine x is equal to 1/2. Y is 1/2, so let's just make that a bit more accurate. So if I was solving this now, and I'll just draw a box, let's say I was solving this in the interval now, we don't want that, do we? That's not going to work. In the interval from 0 to 360 degrees, we can see now that we have two solutions. The first solution is just here, and the second solution is just here. We would get a principal value by taking now the inverse sine of now 1/2. So we would say now the principal value x is equal to the inverse sine of 1/2. So inverse sine, let's write that instead of inverse. Let's just tidy that up, that's a bit messy. So inverse sine of 1/2. In your calculator, sine to the -1, or if you're doing it purely operationally, shift sine. This is going to give me 30 degrees. So shift mode 3 puts me in degrees. I've got a little d there. So I take the inverse sine, sine to -1 of 1/2. You can write it as a decimal or a fraction. Principal value of 30 degrees. So what I'm going to do here is show that this solution is going to be 30 degrees. We now look at the symmetry of the sine curve. The symmetry is going to be just here. So let's go ahead and put that to here. So what we have now is this line. The next one is here. Now that is going to be 30 degrees back from 180. So this one is 150. We can say that the sine of x is equal to the sine of 180 minus x, or if you like, pi minus x. So by symmetry, if we have now one x is equal to 30, then we will have 30 back from 180. So if I was only solving in the interval from 0 to 360, we can see this line does not pass through the sine curve more than those 2 points. So I could say that x is equal to 30 degrees, and by symmetry, x is equal to 150 degrees. Okay, now we can also say that the sine of x is equal to the sine of 360 plus x. So what does this mean? Well, essentially now we're going to have solutions on every 360 degrees. The way I like to solve an equation, and I will set it up like so, is the following. A general solution now, if we were asked to solve sine x is equal to 1/2, this is how I set it up. I start with the principal value and I say that x is equal to the inverse sine of 1/2. That gives me now, using the calculator, x is equal to 30 degrees, and I'm now going to say plus or minus multiples of 360 degrees, and I write that as plus or minus 360n. By symmetry, x is going to be equal now to 180 minus a 30, and you might want to show that in your working, but I'm going to put now x is equal to 150 degrees plus or minus multiples of 360. So this now gives me the general solution to this equation. So for example, if I was going from 0 to 720, all I would do is now add 360 to this one and add 360 to that one. So the next one would be 390, and then we'd have 510, and we'd have 4 solutions. If we were looking at negative 360 to positive 360, we can see we got 2 solutions. So this one I would subtract 360, and this one I would subtract 360. So if we were solving this now, sine x is equal to 1/2, and the interval here, we can say that x is going to be now between 0 and 360 degrees. All I would simply do now is state that x is going to be equal to 30 degrees, and x is going to be equal to 150. Adding multiples of 360 will take me outside that interval, so we don't need them. Yet if I change this, then we would consider now adding and subtracting multiples of 360. So 2 solutions, 30 and 150. So with sine, when you find the principal value, we have the same value back from 180, and then we simply consider multiples of 360 added or subtracted to bring us into the interval. Okay, let's now look at the next one. So if we just now look, y is equal to the cosine of x. So we have 0, 0 here, so 0 degrees, 0 radians. We have 90 degrees, or pi by 2 radians. We've got here 180 degrees, or pi radians. We've got here 270, or 3 pi by 2 radians. And then we've got 360 just here. And then that is 2 pi radians. Again, we can go backwards. You can see these on here. Negative pi by 2, negative pi, negative 3 pi by 2, negative 2 pi. Okay. Let's say we were asked to solve now on here y, what have we got? Y is equal to cos x. So we can say now, let's do cos x is going to be equal to 1 over root 2. 1 over root 2. So what I'm going to do now is go ahead and get a line. What we're going to do is get this line and draw it across. So it's asking me now where this is equal to 1 over root 2. So let's just put 1 over root 2. So 1 over root 2 is going to give me something, give or take, about there. What we can see, if I was solving this now in the interval from 0 to 360 degrees, we're going to have this point just here and this point just here. This time we've got cosine is symmetric, and let's go ahead and put this line on. It is symmetric about 180 degrees, or now pi radians. So in general, I can state the following. Cos x is equal to cos of 360 minus x, and that will allow us now to find these values. So if I did now the principal value, so principal value, we've got now that x will be equal to the inverse cosine, and we'll do this in degrees as initially it's easier to work with, the inverse cosine of 1 over root 2. Again, this gives us a nice answer. If you're not sure of that, shift cos inverse cosine now of 1 over root 2. This should give us 45 degrees. So 45 degrees. So x is going to be equal to 45 degrees. So that is just there. Let's consider now this one just here. By symmetry, we've got the same value back from 316 degrees, so this would be 315 degrees. That is using the property here. And again, we've got now a cosine curve that cycles every 360 degrees. So let's go ahead now and do this more formally. Let's say we were given it now that cos x was equal to now 1 over root 2. And I'm going to say now that x this time is going to be between 0 and 720 degrees. So what we can do is take this and we can write the principal value. The principal value, x, is going to be equal to the inverse cosine of positive 1 over root 2. So we can say that x is going to be equal to 45 degrees plus or minus multiples now of 360 degrees. So x is going to be equal to 360 minus this value, which is 315 degrees, plus or minus 360n. So if we consider, what we're going to have now is the following. We're going to have that x is going to be equal to 45 degrees, but we're interested in this between 0 and 720. So what we can see now is that the next one is going to be just here. So when we jump forward 360, I'm simply going to add 360 to this one. So if we do that, what we're going to do now is 45, then we're going to have 405. Let's now consider that x is equal to 315 degrees. If we think about it, the next one is going to be at 675 degrees. So all I'm doing is simply adding on a multiple of 360, as we're going to be there. So we've got 4 solutions. If you were doing this between negative 360 and 360, we would subtract now 360 degrees off each of these and get those solutions. So this is my approach. We find general solutions given the symmetry. Principal value plus or minus 360. That curve is cycling every 360. It just repeats itself. Then all we do is consider now adding or subtracting multiples of 360 to ensure that we've got all the solutions in the given interval. This is the interval. Okay, let's look at tan. Now, tan is slightly different. Okay, what we're missing firstly are the asymptotes. The asymptotes are at 90, so let's put that just there. Let's move that into place. 90 degrees, let's put that. We've got another one, and these appear every 180 degrees. So the next one is going to be at 270, and then we'll put that one in place. Hopefully you can see these on the screen there, a little faint, but that gives you some idea. That's an asymptote. We're going to have now, clearly we'll have one on the other side, and that will be now at negative 90, and so on. Let's do this. Now, tan equations are actually easier to solve. They're a lot less messy. So what we'll do is the following. We'll put this on, and we'll say that y is equal to tan of x. So y is equal to the tan of x. This point is 0, 0 radians, 0 degrees. 90 degrees, or pi by 2 radians. At this point, tan is undefined. We can't have division by 0, as we saw in the last video, therefore it's undefined. Here we've got now 180, and we've got pi radians. At 180, tan is 0. Another asymptote here at 270, 3 pi by 2. So 3 pi by 2 radians. This one right here is 360, 2 pi radians. So again, this is now negative 90, where our asymptote is or negative pi by 2. We've got now negative 180, so negative 180, negative pi, and so on and so forth. There'll be another asymptote just here. Now, tan cycles every 180 degrees. We can see that. It has a period now of 180 degrees. So the tan of x, let's write this here. So tan of x is equal to the tan of now 180 plus x. All it's telling me to do is simply go ahead and solve this. Right, let's solve an equation. Let's say now that, let's solve the equation. Tan x is equal to 1. So this is going to give me another nice outcome, and I'm doing these to give you some confidence in it. So tan of x is equal to 1, and we'll say now that we want to solve this in the interval. Now let's take this in the interval from negative 180 now, and we will take this to, so x is going to be from negative 180 to positive, should we go for 360? There we go, let's increase our interval. So if we look at that now, where is this going to be equal to 1? So if I just put a line across, so let's just make that a little, that's what we're doing. Okay, so I'm going now from negative 180. So negative 180, so it's going to be 1 just there. There's going to be 1 just there. And there's going to be 1 just there. And we can see these are 180 apart. Now, the way in which I would solve this as a general solution is the following way. So what we've got then, we've got the tan of x. So tan x is equal to 1. We're interested from negative 180 degrees up to now positive, what did we go for? Positive 360. Okay, so all we do then is do the principal value again. Principal value, x is going to be equal to the inverse tan now of 1. This again gives us a nice angle. If you're unsure on a calculator, shift tan, making sure you're in degrees. Shift tan of 1 will give us 45. Principal value, x is going to be equal to 45 degrees. Now all we've got now are plus or minus multiples of 180 degrees. We can see now that it doesn't operate in the same way that sine and cosine does in terms of its symmetry. If we've got one here, we've got one 180 on, we've got one 180 back. So all we need to do then is simply state that x is going to be equal to 45. So we're going to have now 45. If we went forward, we would have now 225 by adding on, and that now simply corresponds to this solution here. And then if we look at this one, this is going to be now 45 minus 180, which is going to give us now negative 135. Really, we should list those out in ascending order. So negative 135, 45, and 225. So there we go. That's my approach. Find now principal value and then just consider these general solutions and fit it into the given interval. So let's go ahead and do some of these. This is as I say, you don't have to do this. The cast diagram is there, or unit circle, loads of different approaches. So let's go ahead and look at solving some equations. So we're asked to give all answers to one decimal place where appropriate. This goes throughout all of the questions that we're going to do. Now these are single angles. In later videos we'll look at compound angles, multiple angles, and all manner of different things. But let's go for this one. So sine x is equal to 0.5, which we've just looked at, and we've got a nice straightforward interval in degrees. So what we've got then is x is equal to the inverse sine of 0.5. So this now is our principal value. So we can say that x is going to be equal to, we've already seen this, 30 degrees plus or minus multiples of 360. We've got now the sine curve, we've got something that looks like this. So if we've got one here, 30 in, we've got one here, 30 back, which is for 150 by symmetry. So x is equal to 150 plus or minus multiples of 360. Therefore, final solutions in ascending order, 30 degrees and 150 degrees. No more, no less, seen it before. Exactly the same here, cos x is equal to 1 over root 2. So we can say now principal value, we can get our principal value. X is going to be equal to the inverse cosine now of 1 over root 2. So x is going to be equal to 45 degrees plus or minus 360n. We consider the cosine curve. The cosine curve now is symmetric about 180. So if we've got one here 45 in, we've got one 45 back from 360, which is 315. So x is going to be equal to 315 plus or minus 360n. We're only interested in this between 0 and 360, so adding or subtracting multiples of 360 will take us outside the interval. Therefore, final answers 45 degrees and 315 degrees. So that's what we get. We've done tan x is equal to 1, so we will leave that alone. Okay, cos x is equal to root 3 over 2. Okay, with this one, what we're going to get now is the following. X is going to be equal now to the inverse cosine of root 3 over 2. This again gives us a nice value on the calculator. It will give us 30 degrees. So make sure you're in degrees. Shift cos now of root 3 over 2. It won't always be the case that we get these pretty numbers, and we will see that later. So x is going to be equal to 30 degrees, principal value, so PV. 30 degrees plus or minus multiples of 360. We're going to have, by symmetry, 30 back from 360, 330, and then we're going to have plus or minus 360n. We're only interested in this now in 0 to 360, so x is going to be equal to 30 and 330 degrees. Okay, things are starting to get slightly more interesting here. What we've got is sine of x is equal to negative root 3 over 2. So what we're looking for is a principal value. Our calculator is going to give us a negative answer as it considers now where the principal value is. It gives a certain period. I'm going to introduce three things here. It's entirely up to you if you use them or not. You certainly don't have to, but it may help. What we're going to do is look at odd and even functions. If we have sine x is an odd function. If we have tan x, this is going to be odd as well. We have an even function, that's cos x. So what we can say on here that sine of negative x is equal to negative sine of x. And you might want to use this, you certainly don't have to. But tan of negative x is equal to negative tan of x. And for our even function, we can say cos of negative x is equal to cos x. You can use that if you want. These are not mandatory, but I think it's important for completeness that I do them. Right, let's have a look at this then. What we're going to have then is the following. We're going to have a principal value. So principal value is going to be now sine to the minus 1. Now sine to the minus 1, x will be equal to the inverse sine of negative root 3 over 2. Okay, this is going to give us negative 60 degrees. What the calculator will do is consider now the cosine curve and its inverse, the sine curve. What we've got is something that looks like this. This now is going to default to giving us the principal value of negative 60. So negative 60. By symmetry, we're going to have one back now, or further towards the y-axis. So this is going to be negative 180. Subtract this value, which is negative 120. So when we do this, principal value is going to be negative 60. By symmetry, the other one is negative 120. Alternatively, how you can think of it is that these have moved on by 360 degrees, and this one here is 240, and this one right here is 300. Don't mind how you want to do it. Again, it's conceptual understanding, entirely up to you. So what we'll do then is shift sine, the inverse sine now of negative root 3 over 2. So negative root 3 over 2, and that gives us negative 60. So by symmetry, remember this point is negative 180, and then we're going to minus that from it. So x is equal to negative 60 plus or minus multiples of 360, and we've got x is equal to negative 180, subtract this, which is going to be negative 120 plus or minus multiples of 360. We're interested in this in the interval from 0 to 360, therefore we would have to add a multiple of 360. So what we could do on the next part is simply write that x is going to be equal to negative, what have we got, negative 60 plus 360, which is going to give me 300, and then we've got negative 120 plus 360, x is going to be equal to 240. If you wanted, you could write this out just here, that sine of negative x is going to be negative sine of x, and we've already seen that we've got here that the sine of 60 degrees is root 3 over 2. It's entirely up to you if you want to use these properties. I generally don't. I simply get a principal value and then subtract or add multiples of 360. Okay, let's look at some others. So those now, again, solve the equation. We're given an interval, and the interval is in now degrees. We're asked to solve the following equations in the interval from 0 to 2 pi, giving our answers as multiples of pi. Okay, we do need to be able to work with radians. I don't like it if a student converts from radians to degrees afterwards. Just learn them. It's relatively straightforward to do, and we have looked at it in another video. So let's look at this one. What we've got then, PV, principal value. So we've got now x is equal to the inverse sine of root 3 over 2. Now this gives us 60 degrees. 60 degrees as in terms of radians is going to give us now pi by 3. Now pi by 3 is going to be now the principal value plus or minus multiples of 2 pi. Just consider what we've got. The sine curve now, if we take it, cycles every 360 degrees or 2 pi radians. So what we've got now is pi by 3, and if you want to, you can do, of course you can do this on a calculator. If we just now change it, shift mode 4, that's now in radians, little radians. So the inverse sine of root 3 over 2, again it's a special angle, and it will give us pi by 3. Remember, what we're now going to have, the next one is going to be pi minus that answer, or 180 minus that, which gives us 2 pi by 3. So we've got one here at pi by 3 and one here by symmetry at 2 pi by 3. Remember, that is pi. So x is going to be equal to 2 pi by 3 plus or minus multiples of 2 pi. We can see by adding multiples of 2 pi, that's going to take us outside the interval, and it will give us these ones. Subtracting multiples of 2 pi again will take us outside the interval, so we're interested in this one at pi by 3 and this one at 2 pi by 3. So final solutions, x is equal to pi by 3 and we got 2 pi by 3. So we're given our answers as multiples now of pi. Sometimes you might see a little c, that denotes that these are in radians. Certainly if we're using decimal answers, I will include the little c. Okay, so that's what we have. So remember, sine of x is equal to sine of pi minus x, and then we got multiples of 2 pi n. We're just adding 360. Okay, let's look at this one. So on this one, we got tan x is equal to 1 over root 3. Again, this is going to give us a nice answer. So x is going to be equal to the inverse tan of 1 over root 3. This is going to give us pi by 6. So if we do shift tan of 1 over root 3, or if you want root 3 over 3, this is going to give us pi by 6. So principal value now, we can say that x is going to be equal to pi by 6. Now remember, with the tan curve cycles every 180 degrees. So all we would need to do on here is add multiples of 180 degrees. We saw if we had one here, we had 180 on. Now 180 is going to be pi radians. So what we can say is plus or minus pi n. So we're interested in this now from 0 to 2 pi. So what I'm going to have then is x is going to be equal to pi by 6. Now we need to add another pi radians on. So that's going to give me 7 pi by 6. I'm just adding 6 pi by 6. If we consider adding another pi radians, this is going to take me to 13 pi by 6. 12 pi by 6 is going to give us the 2 pi, so that would be outside, and we would see that this one is going to be somewhere here. So that's what we want, that's what we're interested in. Again, if you wanted, you could just now add pi to that if you're not comfy, 7 pi by 6. If we added another pi to that, we would see that that is going to be 13 pi by 6, which is going to be outside. 12 pi by 6 is 2 pi. Okay, let's look at the next one. We've got now cos x is equal to -1/2. Now with this one, what we're going to have is the cosine curve. The cosine curve looks something like so. So it's going to pick one up just here, and it's going to pick one up just here, the same distance back from 360 or 2 pi. So what we can do now is write principal value. So principal value, I don't have to write principal value. You see, I'll sometimes write it. It's not mandatory. So x is equal to the inverse cosine now of -1/2. If you're unsure, that's perfectly fine. We can do that in a calculator, and we'll do the inverse cosine now of negative, and you could write that as a fraction or decimal, -1/2. So this gives me 2 pi by 3. So that now is my principal value. So let's write this in. So x is going to be equal to 2 pi by 3 plus or minus multiples of 360 degrees, or 2 pi. If we just considered that one, we got one 360 on, and we're going to have one 360 on here. And then this one is going to now be 2 pi by 3 back. We're interested in this one from 2 pi. Or if you like, it's this angle subtracted from 180. So all we're going to do then is 2 pi, if you're not comfortable, minus the answer, and that gives 4 pi by 3. So 4 pi by 3 plus or minus multiples of 2 pi. Now when I say multiples of 2 pi, there's the next one. The other one's 2 pi back, and so on and so forth. So clearly we're only going to have two solutions in the interval, 2 pi by 3 and 4 pi by 3. They are multiples of now pi. Okay, last one, tan x is equal to 1. So principal value again, x is going to be equal to the inverse tan, so inverse tan now of -1. This is going to give us now negative pi by 4. So let's just put this in. So shift tan of -1, and that will give us negative pi by 4. Again, you could have used the odd and even functions. I try and stay away from them initially, as it's more to learn. But what this has done now is picked us up the one just here. Okay, this has picked us up now -45, or negative pi by 4. Remember, the tan curve cycles every 180 degrees. So what we're going to do is just add pi to this. So what we can say then is that x is going to be equal to negative pi by 4 plus or minus pi n. We're adding multiples of 1 pi, not 2 pi. We've already seen now the cosine and sine cycles 360, tan cycles now 180 or pi. So we're going to have x is going to be equal to, if I add this on, 3 pi by 4, which is going to be the next one. And then we can add now another multiple. Now if I add another multiple, so add in another multiple, that is going to give me now 7 pi by 4. That is still in the interval from 0 to 2 pi. 8 pi by 4 is going to give us that. If you're unsure, all we're going to do is add shift pi, 3 pi by 4, add another pi, and that's going to give us now 7 pi by 4. If I added another one, let's add now another multiple of pi, that's 11 pi by 4, which is certainly greater than 8 pi by 4, which is not what we want. So final solutions, we've got these now in the given interval. If it was between negative 180 or negative pi and 2 pi, we could include this negative pi by 4. Okay, so there we go, working with radians with these exact values. These are our special angles, and I always start with these because I think it's just slightly easier to deal with. Okay, let's look at some others. Right, solve the following equations for x between 0 and 360 degrees. Okay, these are not going to give us nice values, and this is where I use a calculator. I'm going to find a principal value, by symmetry find the next one, and then simply consider multiples of 360 on from there. So what we've got then on the first one is the following. So we've got now that the principal value, so PV, x is going to be equal to the inverse sine now of 0.24. I've got no idea now what this is going to be as an answer in degrees. So shift mode 3 back into degrees. Shift sine now of 0.24. That gives me 13.886 and so on and so forth. Right. What I'm going to write then is x is equal to 13.8 blah 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 plus or minus 360. And nothing's changed. All we've done here is simply solved this equation, and let's draw this. There's a sine curve. I've got one just here. That's going to be my 13 point blah blah blah. then we're going to have 180 minus that. At this stage, again, you might see this to be completely pointless, but when we get on to more complicated double, if we got a double or compound angle here, I'm going to store this in the calculator as A. We don't need to for this particular one, but I'm going to anyway. So what we're going to do is write that. What I'm doing then is hitting Shift Store A, especially if the level of accuracy we need is high and we're doing multiple calculations. 180, and we could press minus the answer, or we could press recall A, and that is going to give me 166.11 and so on and so forth. 166.1 ... plus or minus 360n. I'm going to store this in as B. Again, we don't need to, but if I had any other calculations, which we'll see later, then we can always call these back rather than truncating answers. So if we look at this, I can quickly bring back A, which is 13.9 to 1 decimal place, and I can quickly bring back B, which is 166.1. So we asked originally to give these to 1 dp, so x is going to be equal to 13.9 degrees, and we've got x is equal to 166.1 degrees. They're to 1 dp. Sometimes you'll be asked for 3 significant figures, sometimes it'll be 1 dp, 2 dp. I'm not really interested in that as such to begin with, I'm just looking at the actual approach. And the reason I've done this is if we were, for example, solving the sine of x minus 24.2 degrees is equal to 0.24, at this stage what we'd have is not just x, but we'd have x minus 24.2. So by storing these and then adding and subtracting as required just keeps it nice and clean. In the next video we will look at these where we have now this compound angle, x minus something or x plus something. Again, nothing to be worried about, exactly the same approach. All we're going to do is consider solutions for this and then go ahead and solve. Okay, let's go on to cos x is equal to 0.83. So let's look at this. So x is going to be equal to the inverse cosine of 0.83, and that is going to now be in a calculator. So shift cos, we're already now in degrees mode, shift cos of 0.83, and that gives us now 33.9. So x is going to be equal to 33.9 blah 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 plus or minus multiples of 360 degrees. With the cosine curve, by symmetry, we take this value off 360, and that will be our next one. If you want to show that and you're working 360 minus this, you can do. Again, I don't need it, I'm just going to store it, and then we can do 360, and this time I'm just going to do minus my answer. So we've got now 326.098, so 326.098 blah 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 plus or minus 360n. So nice and straightforward. Now if we just look at this, we can see now, and I don't know, like writing this down, I'm not quite sure what comes after this in terms of rounding up, but remember it's in there. So 33.9 degrees to 1 dp, and then this one is going to be 326.1 to 1 dp. So they're given, and I might write that there. It's not mandatory. Okay, let's look at the next one. This time we got 3 tan x minus 1 is equal to 2.12. As in algebra, let's say I've got, let's go for 3p minus 1 is equal to 2.12. Add 1 to both sides, 3p is equal to 3.12. Divide both sides by 3, what's that going to give me? 1.04. We would do exactly the same here. All I want is an expression for tan x. I don't want 3 tan x, I don't want 5 tan x, I don't want tan x minus 10, I just want tan x. So what we've got then is 3 tan x minus 1 is equal to 2.12. Adding 1 to both sides, 3 tan x is equal to 3.12. And then tan x, dividing both sides by 3, is 1.04. Remember, for sine and cosine can be between negative and positive 1. Tan can have any value. So Perfectly fine. So let's go ahead and look at principal value. Principal value is going to be the inverse tan of 1.04. So x is going to be equal to the inverse tan of 1.04. Don't know this one, so calculator time. We're in degrees mode, and it's shift tan of 1.04. Principal value 46.12. So let's write this down. So x is equal to 46.12 blah 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 blah, plus or minus multiples of 180 degrees. Remember, tan, just adding and subtracting 180. So to 1 dp, remember we're in the interval from 0 to 360. So x is going to be equal to 46.1. That's going to give me what, 226, so 226.1. And again, if I add any more multiples of 180, that will take me outside the interval. So 2 solutions in that interval. Okay, let's look at this one. Right, this one looks a little nasty. So dividing both sides by 4, sine x is going to be equal to negative, what's that going to give me? 0.27? That should, 1.08 divided by 4 is 0.27. Let's just, 0.27. So let's go ahead and write that. So it's equal to negative 0.27. So principal value, this is going to give us another negative answer. Right, so here's my approach. X is equal to the inverse sine now of negative 0.27. What this is going to do again is do something like so. Sine is positive now, and then we'll take the negative values. We're going to get this one just here, and by symmetry, this one just here. You can just consider that it's going to be now 180 plus these. Okay, right, x is going to be equal to. So what I'm going to do now is take the inverse sine, shift sine. Inverse sine of 0.27. That is going to give me negative 15.664. So negative 15, so negative 15.66 ... plus or minus multiples of 360. Okay, I'm going to store this as A and just write above it I've stored it as A. Easy enough with this one, don't need to do it, but later on you'll see how beneficial this can be. Shift store A. By symmetry, what we're going to have now is negative 180, subtract that value. So negative 180, and then we're going to subtract the answer, or if you want, you can just put A in, and that gives us negative 164.3357. So negative 164.335, blah, 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 plus or minus 360n. Okay, I'm now going to store this as B. You don't need to. Let's just put this in. Shift store B. So that's B. So I'm keeping the accuracy by doing this. So if I consider what I'm going to have now the following. We could just put plus 360 here, but what I'm just going to put is B plus 360 degrees will bring me back into the interval, 195.7. So x is going to be equal to 195.7. If we now consider the next one, these are stored in, so all I'm doing is recall A plus 360 degrees. And that's going to give me now to one decimal place 344.3. So 344.3, and they're both now to 1 dp. So that gives us our 195.7, and that is going to give us our 344.3. Entirely up to you. You might, again, think that's long-winded. Right up to you. I prefer just to store them in, so I don't have to do the calculation again. For example, now if we had, let's just write one out. This is really quite possible. Sine of 3x minus 41.6 is equal to, let's go for 0.14. So what we'd have now is 3x minus 41.6 is going to be equal now to the inverse sine of this. If we just do this, let's just do the inverse sine of that. So 0.14 was it? Let's write that down. Okay, so what that would give me now is 8.04. So if I stored this in as A, shift store A, then I did now the 180 minus that answer, that's going to give me B, and I store that now as shift store b. If I wanted to find now the value of x, what I could do is simply say recall a plus 41.6, and then I would divide that answer by 3, and that gives me that. And if I wanted, I could call that shift store c. Remember, I've got b here, so with that one I would add the 41.6, and that would give me that. I would divide that by 3, and that would give me x. If I want, I can store that now, shift store d. So remember, a is still there, b is still there, c, which is the first answer, assuming I was in now this interval from 0 to 360, and then we've got d. The only difference here is that when we've got plus or minus 360n, at the end here, when we're dividing by 3, we'd have to divide this by 3, which would give us multiples of 120. So all subsequent solutions to this, if we just bring up c, then the next one is going to be plus 120 degrees, because we got 3x. And then that would give me that, plus another 120, which would give me that. And then you could see another 120 would go outside. Yet if we took d, I could just add 120, and that would keep it now to 191, plus another 120, and that would give me now 311. So I've solved quite a tough equation by simply using these. I've still got them all stored in, and again you just overwrite them as you go. Not expecting you to understand that. I've not done it clearly or fully. I'm just showing the benefits of storing these values in the calculator to ensure that we've got now a high level of accuracy. Right, let's go on. Okay, we're asked to solve the equations now for x between 0 and 2 pi. So we're back in radians. So first thing, shift mode 4. I always like these calculators. They're nice and straightforward, but do make sure you're in the correct mode. So let's go ahead and look at this. So the first one, x is going to be equal to the inverse cosine now of negative, what have we got, negative 0.54. Again, I don't know this one, so I'm just going to find the value. So shift cos now of negative 0.54, and this will give me a principal value. 2.141. So x is going to be equal to 2.141 ... plus or minus multiples of 2 pi. This is a cosine problem, so what we've got then, if we've got one now 2.14 in, which is going to be just here, we've got that the same distance back from 2 pi. So if I do that, again, don't need to do this, shift store a, it's just a habit. What we're going to do is 2 pi, let's press shift pi, 2 pi minus our value of a, and that's going to give us now 4.14. So x is going to be equal to 4.14, and so on and so forth. So let's just get that. So let's just check that. So shift cos, let's check I've got it right, 0.54. That gives us a 2.141. And then if we do 2 pi minus that, that looks good. And then for 4.1. Okay, so again, plus or minus multiples of 2 pi. So the next ones, remember, this is going to cycle here and here. We're just adding 2 pi to that one. And then this one, we're adding 2 pi, but we don't need to do that because it's only in this interval. So x is going to be equal to 2.1 radians. Now, I'm giving this to 1 decimal place as it was stipulated initially. Again, you might have 3 significant figures. So that would be now the 2.14. And then what we're going to have is the 4.1 radians. I'm using that little c to denote radians. Okay, tan x is equal to 3.7, so x is equal to the inverse tan of 3.7. So again, we're in radians already, so shift tan, the inverse tan of 3.7, 1.3. Okay, so x is going to be equal to 1.30 ... plus or minus multiples of pi. Remember, all we've got now are just multiples of pi. So what I'm going to do is say that x is going to be, again, we're doing this to 1 decimal place, 1.3. Then we're going to add pi to this. So if I do that, remember pi is 3.14, 159, and so on and so forth. If you want to, you can store this. I don't think you need to, just in case you mess it up. Plus now a multiple of pi. and that's going to give me 4.4. I think again these would be better to three significant figures. Okay, and we're interested in this now between 0 and 2 pi. Now 2 pi is just two lots of 3.14, so you're looking at what, 6.29 or something or other. So let's just look at that 2, what's that going to give us? 2 pi. So if you want 6.28, so of course we're getting some idea. That's now at 360 degrees in radians, 6.283 radians. So for example now, let's just bring back a 1.3. If I added now two lots of pi, we would see now that gives us 7.5, which is 7.59, which is clearly outside. Okay, this one right here, let's go ahead and do this one. So what we've got here is 1 minus sine x is equal to 0.43. So adding sine x to both sides and subtracting the 0.43, we can say that sine x is equal to 0.57. So all we've done is rearrange that one, and nice and straightforward from here. X is equal to the inverse sine of 0.57 radians. So it's the inverse sine of 0.57, which will give us our answer in radians. So shift sine of 0.57. That's going to give us 0.60. Again, don't need to store this. So x is equal to 0.606. What is it? 5 ... plus or minus multiples of 2 pi. And then x is going to be equal to pi minus this quantity. Remember, sine curve, if we've got one just here, then we've got the same distance back from pi. It's symmetric about this point. So that's 0, that's pi. So what we've got then, that's stored in as the answer. Then we're going to do now, so shift pi minus that, and that gives us 2.535. So let's write that 2.535 plus plus or minus 2 pi n. So now we've got x is going to be equal to, again, I think this would be better three significant figures, which would be 0.607, but to one decimal place, 0.6 radians, and then we can have 2.5 radians, or if you want to three significant figures, 2.54 radians. Nothing else in there. Okay, let's look at the next one. We got 2 cos x is equal to sine x. Now, this doesn't look ideal. When we're dealing with an equation like this, ideally we should have one trig ratio. Now, when we're talking about one trig ratio, we either want sine, cosine, or tan. I'm going to write to the examiner now that I know what I'm doing. I'm going to write now that sine x over cos x is going to give me tan x. That is an identity that we saw in the last video. We'll come on later to look at an example. So I'll just leave this alone for now. Let's say I had 2 cos x sine x is equal to sine x. I may as well introduce this now because when we come on to it, it's important you know. A big error here is to divide both sides by sine x. We can divide by one of these trig ratios to get an identity, but if I divide now by sine x here, I have the potential to lose a solution. So what we'd have here is 2 cos x would be equal to 1 if I divided both sides. Cos x is equal to 1/2. I'll do this in degrees. Inverse cosine of a half, x would be equal to 60. And if we were doing it between 0 and 360, the next one would be at 300. But what we should have done is written 2 cos x sine x minus sine x is equal to 0. Taken out sine x as a common factor and then got 2 cos x minus 1 is equal to 0. Now this is what we've just solved, but we've also got sine x is equal to 0. Now if we look at the sine curve, we've got something like this. So we got sine x is equal to 0 at 0, at 180, and we got 360. So I would have missed 3 solutions in the interval from 0 to 360 if I just divided. So here we would factor. With this one though, we can just divide, and we can write that 2 is equal to sine x over cos x. I would show that. Therefore, what we can say now is 2 is equal to tan x. At this stage, we have a straightforward scenario. So x is equal to the inverse tan of 2. So inverse tan of 2, and we'll do that on a calculator. Again, we're working in radians. Shift tan of 2, principal value 1.107, so x is equal to 1.107, blah blah blah, plus or minus multiples of pi. Again, tan is cycling every pi radians, so all we would need to do, we're interested in this between 0 and 360, or 0 and 2 pi, so 1.1 to 1 decimal place. We're going to be adding now pi, so add pi, 4.2, again, I prefer these to 3 significant figures. And if we consider adding another pi, we're going to quite clearly go outside that interval. So add another multiple of pi, that takes us to 7.39. So we've only got those 2 solutions. Something interesting, if you really wanted to do this, is if you drew the curves in this interval. Sine looks something like that. So that's y is equal to sine x. And then if we had 2 cos x, what we would have is something that looks like this. We would come down like so, and then come back. Let's bring that down a bit further, and it would do something like that. That's not brilliant, but it gives you some idea. So we've got 1 point just here and 1 point. That's what it's saying. We could solve those graphically and see there's 2 solutions, but it's easier to write it as a single trig ratio, and that now is in tan. So there we go, 56 minutes of solving trig equations. I like to get this essentially a general solution and then consider now what we're looking for in the interval. It works for all of the trig equations we're going to come across, and we need to be comfortable with them in terms now of both the degrees and radians.